Our first topic will be some introduction to the basic assembly instructions and basic debugging and the different conditional jumps. So let's copy to the machine our sample application. It is on the DVD. Self, examples, malware, and we start with the patching 01 example. I copy paste it to the C root. And let's try to examine this application. Oh, first of all, I show you the application source code, because now, of course, we have the source code as well. In real life, we are not so lucky, obviously, but now we are only practicing. So we have the source code, and let's see what does this application do. Here it is. It's a simple application. It will queries a number from you and read it. And after that it will check if the number is 0. If it is 0, then it will print 0, otherwise it will print non-zero. And our purpose is to modify the application behavior to work exactly on the opposite way. So if you write here some number which is not 0, then it should print 0, otherwise it should print non-zero. And of course we should modify the exe file, not the source code. First of all, let's check if the application is working. So I just go to a command prompt, enter to this patching 01/release directory. Here is the patching 01 exe. I type a number which is not 0, print non-zero. Then I write here 0, print 0, and write here a negative number. It's really non-zero. Okay, fine. The application now works as expected. Let's try to change the behavior. And how to do it? First of all, we try it with the OllyDbg, the 1.1 version. You go to the OllyDbg.exe and file, open the application. It's in the C, patching 01. Patching 01 release patching 01.exe and open it. Here starts the application with some nice call instruction, and after that a jump instruction. If you create some Visual Studio application, then practically all of them starts like this. This first call used to be some security cookie initialization, and after that the jump will jump to the main. Sorry, not exactly to the main function, but the beginning of the code start. So we just, on the first line in this call, I know now that it is unimportant for us. So I just go to the debug menu, and there is the step into and step over command. The difference between the two one, if you are standing on a call instruction, the step into will enter into the call instruction, and you can examine the instruction within that function one by one. If you press the step over, the F8, then you will execute the call as one instruction, so you will not see the detailed instruction within that call. Now, because I know that this first call is unimportant, I will just press the F8 button. Of course, in real situation, you have to start to examine every call step by step, and it takes a bit longer time. But now I want to speed up it a bit. And I press the F8 button to run the whole call. Then here is a jump. It will jump somewhere closer to the beginning of the code. I make it a bit bigger. And here is the application, and as you can see, there are many call instructions here. Practically one of the call instructions will start the real main function. I don't know now which one. Of course, I can examine the calls. For example, this one calls the kernel 32.sleep. Of course, it cannot be my main function, and I can continue like this is some message exit in the msvcr90. It cannot be my main function, and so on. So practically I have to start step by step on the instruction by the help of the F8 command, and when I arrive to a call, I have to examine if it can be the main function or cannot be the main function. For example, this first one, to be honest, it's really at the beginning, so most probably it is not the main function, but it points to my executable area, so it is also my code, not some kernel 32 or NTDLL or some Windows API. So maybe it can be, but now because it is too close and I know this application, I will just press here the F8 button. And I continue the run. It will arrive to the next call. Now I again have to decide to press F7 or F8, because it's pointing to the kernel 32, it cannot be my main function. It's written what it is. So I just press here the F8 to continue the running. Then I continue. It was jumping again. Here is another call. It calls the MSVCR90. So it cannot be my main function. So I just press the F8 and continue. Here is also a call to the MSVCR90. It's again not my executable, so it cannot be the main function. So I just press the F8 again. Then continue. Here is another call, kernel 32. It cannot be my main. So just press the F8. And here is something. It will call the patching 01 04 10 00. Maybe it is my main function. Now I know that it is my main function, of course. It points to my code, like the first call, and it is a bit further, so most probably it can be a main function. I have no better guess now. So I want to enter into this call, so I press the F7 instead of the F8. So just press the F7 and I enter to this main function. And as you can see, here are some print. It will set up some strings. And after that it will print the messages. I continue the running by pressing the F8 button. Call ESI. It's written here, it will call the printf function. If I come to the command window, I see now it is empty. If I let this call ESI run and I come back here, really, the first text is printed. Now I continue the run. It will push some other text and again call the printf function. And if I take a look at it, type number really printed. Then I continue the run. Now it will run a scanf function to read something from the screen. If I press the F8 button here, then nothing happens and the program went to running state. It is waiting for me to enter a number. I will enter, for example, 1 here, not 0, that's the important point, and press the enter button. Then it arrives back to the code. Now I have to start the examine because, as I mentioned, we want to change the working behavior of the program just exactly to the opposite. So we have to start where does it examine this number. And we can see here CMP, a comparison, and the jump instruction just after each other, those two. Most probably if you are hunting for those kind of things like branches, for example in this case, then you have to hunt for those kind of instruction like comparison and after that some conditional jump, some kind of jump, conditional jump instruction like jump if 0, jump if not 0, jump if equal, jump if not equal, jump if equal, or something like that. Jump if below, or whatever. Let's examine those two instructions. The CMP, that's the comparison, it's nothing else but a subtraction, practically. So this CMP ESP plus 4, 0 can be translated for you as sub in square brackets ESP plus 4, 0. What is the difference between the CMP and the sub? Then the difference is that if you write the sub instruction, it will really subtract the value. But if you use the compare, then it will only modify the registers. Like that it will run the sub instruction, but in reality it will not store the result of the subtraction. So it's at the background, those are the same instructions, but in case of the sub, the result is stored. In case of the CMP, the results are not stored. only the flags are modified like if it were done. So I just start to press the F8 button. F8, it will do the comparison, F8, and if I take a look at the flags, it will show me that the ENO, EMB, ENE, EA above, jump not signed, GPO, jump greater or equal, and jump greater instruction were run in this case. As you can see, it is written jump is taken, it will jump. Here is a JNZ, so jump if not 0 instruction here. You cannot see this one in the list. But this one is exactly the same like the JNE, so jump if not equal instruction. If you search for the assembly table, here is the assembly instruction JNE, jump if not equal, which is exactly the same like JNZ, jump if not 0. Both of them checks if the 0 flag is equal with 0 or not. And the machine code of it is 75 or 0F85. That's why it is written in one place JNE and the other place JNZ, but they are the same. What is the opposite of the JNZ instruction? Of course, the JZ instruction, the jump if 0, and the machine code of it is 74. So practically, we will have to change this 75 here to 74 to get the exact opposite behavior. Let's try to do it. You can do binary edit, but in Olly it is not necessary. You just right click here and select the assemble, or just press the space button when you have selected this line, space, and change it to GZ. And click on the assemble button, and it is changed, as you can see, immediately to GE. And as I mentioned, the GE is exactly the same instruction like the GZ. So no problem, did it correctly. And now let's try if it works as we expected. I wrote here the number 1, so theoretically now if I let the application run, it will print that it is 0. Oh, one more thing, I will memorize this memory address, this 010410-2E. So I just let it run, exit code 0, so finished, and really the 0 is written, but as we can see the 1 is not 0. So we were able to make this application to run exactly in the opposite way like it's supposed by the application developer. Of course, in real cases, when you analyze malwares, why you need it? Because there will be many traps in the malware application. For example, it wants to sense if there is a debugger and want to make it more difficult for you to analyze the code, do some false calculations, but in reality doesn't need for the application, just they are there to waste your time until you analyze, and practically you want to kick out those codes like this. But in a real malware, as I mentioned, there will be many such a code, so most probably you want to automate this process because you don't want to write every time manually, you don't want to change the program code because it's just time consuming. How to do it? I restart the application. Okay. And let's go again to the same position. So I start to press the F8 button until I arrive to the same place. I press the F8. Here is my main function calling. I press here the F7 and start to continue. Scan F, it will read the number, for example 1, and I mention you to try to memorize the address. It's here. So the application should be changed at the position 010410-2E. Oh, first of all, how we can do it automatically. That's why we installed this OllyDbg script plugin. If you open the script window, you are able to load here some script and you will be able to run them. So let's try to write some simple script which is able to patch this application. How to do it? I go to the OllyDbg directory and I write my script here. Just create a new text document. I will call it as P1 because this is the patching 1 example, and it will be txt file, and enter. If you want to learn the programming of the OllyDbg with this OllyDbg script, and when you download the application, just a moment, I go back to the Olly plugin directory to show you. So if you download this script, here is an OllyDbg script.txt file, and if you scroll down, here the different instructions what you can use are written and explained how to use them. The first instruction we are going to use is the JNE instruction. By the help of this instruction, you can get some information about a module, for example now from the kernel 32 module, and what we are going to get is the module base address. Why? Because maybe the operating system uses some address space layout randomization, so the next time it will load to a different address. So we have to calculate always the position what we want to modify at runtime. So first we query the module base address. So the first instruction is something like JNE. We search for the application patching 01 because that's the name of our application. If I come back here to the memory windows, here you can see the module names. More exactly it is patching because this version of the Olly not use all the characters of the name, so it will be enough. So patching, and comma, we will query the module base like it is written here. Fine, after this first line we got the module base address. Where is the result? The result is stored, if you read this file, somewhere in a so-called $result pseudo variable. So practically you have to save the content of this pseudo variable. How you can save it? You have to copy it to another variable. It can be done by the mov command. As you can see, this OllyDbg script language similar to the assembly practically. So I will move this result to a variable called other, and it was in the $result pseudo variable. I want to move it to another place because every instruction will modify this $result variable, and of course even after this move the content of the $result is not the module base address anymore. After that, just to show you, there is another instruction, it is called log. You are able to print some log information to the log window if you press the L button here. Then you can see here the log window, and you can write there some messages for yourself or somebody who is using the same script, and I will log this address. It will give you the module base address. So if you take a look at this memory map, it will give you the PE header starting position. This is the 01, 04, 00, 00. So it will be the module base address. But you want to modify the instruction at this position 01, 04, 10, 2E. So fortunately the relative distances will be always the same. So even if the application loader will load this exec to a different memory base address, then the relative addresses will be still the same. So this 10, 2E difference will remain the same. So I have to calculate practically. Where is my calculator? I change it to scientific view and hexa. I know that I have to change the instruction at the position 01, 04, 10, 2E. 01 04 10 2E, and the base address is 0104 0000. So I subtract from here 01 04 0000. It's equal 10 2E. So I have to add, this is our next instruction, to this address variable 10 2E to get the position where I want to modify. And how to modify the code? It's very simple. We have to move. So use again the move instruction. Move instruction to move some data to this position. But here you have to be careful, because if you write something like this one to move here the 74, it will not be good. Why? Because then it will move this value 74 into this variable. I don't want to do it. What I want to do is to take this variable as a pointer, and where it points, it will point to this position exactly, to this 01 04 10 2E, and I want to write to this position, so it is an indirect writing. So instead of the move order, I have to use the square brackets here, which is the indirection. And there is one more problem. If you write here 74, then it will take it as a 4-byte value, because it's a 32-bit application. I have to put hash marks around it. It will tell the debugger, sorry, it is only a 1 byte, so please do not extend it or whatever. It is exactly as long as written here. If you use this hash mark, you have to be careful, because you are not able to write something like this one. You always have to write even number of characters here. Okay, so we will move to this position, the value 74, and save this script. Now let's try to use it. Go to the plugins, OllyDbg script window, here it is, and right click, load script, open. It's in the OllyDbg directory, p1.txt, here it is. As you can see, the first instruction is already run, and it gave us the result 10 40 0000, as I mentioned. It's exactly the same like the starting of the PE header of the patching application. You can run the script by pressing the tab button. It will do one instruction from the script. So I just start to press the tab button, tab, then the second the instruction run, then tab again, it printed to the log window the address. It's really printed here. Tab again, I will add to the address this 10.2e value, and now you can start to watch this position. It should change from 75 to 74, and really it changed to 74. So we were able to write a simple script, but you can just run until the cursor run the whole or whatever, or step by step run it. And it is capable to modify this application to work exactly on the opposite way like it is expected. And it's a very simple solution, you don't have to do it manually again. And if I press the run button, it really works on the opposite way. Of course, you can use it many times, try to like restart, come here again, just run it. Run the application, write here some number, and as you can see it works opposite. So you don't have to do the manual work. Let's try to do the same thing with Immunity Debugger. So I go back and open the Immunity Debugger file, open, go to the C patching release, and here is this patching 01.exe, open it. As you can see, It's practically an OllyDbg again, because the immunity is some extension to the Olly. And you can press again the F8 button, because I know that the first call instruction is the setting of the security cookies, so it is not important for us now, because it is a Visual Studio application. Then there is a jump. It will start the application. It's nicely colored now, simpler to run. Still not the main function. Still not the main function. It is maybe the main function, because it points to our application. I just press the F7 here to enter to this call, and I am here. Again the same instructions. And the printf was running, it's really printed. Again, the second printf was running, it's really printed. Then it wants to read some data from the screen. Okay, I will write here 1. And as earlier, here is the CMP JNZ, so some comparison, and after that a conditional jump instruction. This is what I have to hunt if I have to kick out some branches. Okay, again of course I can do the right click, assemble, and modify the instruction manually, but some manual work, so better to just write a script. The advantage of the Immunity Debugger, it can be scripted in Python, and many people can program in Python, so maybe you will feel it easier than to do it in OllyDbg script. You have to go to the program files, Immunity ENC, Immunity Debugger, and PI commands. There are a lot of Python scripts. You can take a look at some of them to learn how to write such a script. I will try to introduce or show you the basic ideas practically. We create here some new Python script. It will be called as P1 because this is batching 1.py. Oops, sorry, py. It's created. Right click, open with, not with Python yet, but with a notepad to edit it. Okay. And let's try to write our script. We will start, oops, I will change the font to use some bigger one, it's maybe better you to see it. So we will start with the import imlib command. It will import the necessary Immunity Debugger libraries, what we have to use. And after that, we will define a main function, def main. And this main function, main, and this main function will require or will get some arguments, so args. I forgot here, you have to end it with the column. As most probably you know, in case of Python, you have to show the different blocks, for example, in case of cycles or if or procedures or functions or whatever, by the help of either indents. That's why you have to be very careful. I write here 2 spaces, not a tabulator, not whatever, because if you start to mix them, because for example you write here 4 spaces and your text editor change it to tabulator, then the Python application maybe will not run after that because the tab is not the same as the spaces. So it can cause you some problems. Our first task here in the module is to create a debugger object. It can be done by the imlib.debugger. In brackets, we will call this function. And the result of it will be stored in the im variable, so practically we create a debugger instance. Then, again, as we did it earlier, we have to find the base address of the module. It can be done on the following way. We create a module and by the help of this im object, and we just query it for the get module to give a module to give us the patching.exe. Patching01.exe. It will give us this module. And now we have to get the base address of this module. So my base, for example, equal module dot get base address in brackets. So in this main base variable there will be the base address of the module. Of course, if you want, you can do some logging. For example, you can use the im.log command. It will write again to the log screen. If you press the L button here, this is the log screen. So again, just to show you, I write here some logging. For example, I write here base address. And it will be 0x because it will be some hexa value. And I print here in 8 character some data. And what data? This my base variable. So it is something like a format string, just instead of the comma you have to use here the percentage sign, but otherwise more or less like the printf function, for example in C. Then we have to calculate the patch address. The patch address is nothing else but the base address, so this my base, plus 0x10.2e, as you remember, or you don't have to remember, just come back here and check. It is at the 010410.2e, and if you take a look at the memory window, the base address now is again 01040000. So we have to add 10.2e to the base address to get the address where I want to patch. Again, just for the fun, we will print it to the log screen. It will be the patch address. And it will be 0x, so some hexa value. It just print 0x, nothing else. And after that I will put here the value. This is percentage 08, so 8 character long x hexa value. And I want to print here the patch other variable. Yes, it's printed. Okay. The next, we have to create the patching code. It can be done by the help of patch equal, and we will create the code by the help of im.assemble. So we will translate this code, and we will translate the assembly instruction db74. Why db74? Because we want to overwrite only this 75 here. We don't want to touch this 0f. So practically you have to overwrite only the type of the jump and not the parameter of it, because if you touch the parameter it will jump to a different place. So we don't want to touch it. And in case of assembly, the db74 means practically byte 74. So it's, don't care what it is, just put there the value 74. And we can write it to the memory. So im.write memory, and in brackets we have to give which address. To this address I want to write this value, that's all. And then I have to return with some messages. for example with OK. Of course, you can write here some if to test if it was able to query the base address or not and things like that. But now I wanted to keep the script as simple as possible for practicing. And let's save the script. Save it. Because we saved it to the correct position, program files, Immunity, ENC, Immunity Debugger, PI commands, here it is. We can just run it by typing exclamation mark and P1. This is the running of it. The .py doesn't need, so you just P1. And we can start to watch this JNZ 75. It should change to GE or GZ if it's better for you, as we expected. And we can run the application, and really for the one printed that it is 0. Now you can debug, restart the application, and again just run this patching code. It prints the OK message here. And if you run it, the already patched version is running. So for example to -1, it will print you the 0 again. It works exactly opposite like earlier. If I restart it again, run the patching, run the code, right here 0, it prints non-0, so exactly the opposite. So this is how you can script the Immunity Debugger. Of course we will do it a bit more and many other instructions. And the next debugger will be the Windows debugger. Right, just go to the WinDbg and open it. First of all, if you just open here the executable and go to the C patching 01 release patching 01, yes, then it opens it, but as you can see it's not as nice as the Immunity and Olly and whatever. You are not really able to see many information like printed there. So what do we have to do? We restart the Windows debugger, and go to the file, open workspace in file. And if you go to the themes, there are some pre-created themes which gives you some arrangement of the debugger, but more simpler to use according to my opinion than the original simple interface. What I choose from those many different themes is the standard VS, but of course try all of them, and which one is the best for you, that just use that one. Open it. Here is a window, like do not close this window because it is a point of reference. Okay, we do not close it, but we make it a much smaller because it just wastes our space here. So I closed it as small as possible. Unfortunately, I cannot make it smaller. So this is the window now. And now if I open this executable again, so here is this patching 01.exe, and open it, it's much nicer now. Now it looks like in case of Olly there is some disassembly window, there are some information, there are some commands and whatever. So the main difference between the, not main difference because the Olly can be set other way as well, but by default the WinDbg stops not at the application entry point like the Olly did, but at the Windows loader application when it loaded the exe. It has of course many advantages and some disadvantages. The advantage of that, some applications do some anti-debugging techniques like the TLS callbacks and things like that. When it wants to run some code, even when it is loaded to the debugger before the debugger starts to debug it. And in case of the WinDbg it is not possible. In case of the OllyDbg, you can change it. For example, in case of the Olly 2, go to the options, and here you can click to this start, and for example to stop at the TLS callback if defined, or at the main module, WinMain module system breakpoint, so you are able to set it differently. Now, because this application will stop at this system breakpoint, we have to let it run until the Windows entry point where we were last time, so practically the entry point of the exe application. Let's see how to do it. First, use the command lmf m, and after the name of the exe, like patching 01, and it will print you the base address, so this one. And now we want to know where is the application entry point, so we can print by the !th command, and after that this module base address. Oh, sorry, Sunlight doesn't want to copy it. Ctrl C, Ctrl V. Now it's working. And it will print you some information. And if you scroll to the top of it, here was my command, and just try to scroll down, there will be the optional header values. Those are the optional header values of the exe file, which are practically not really optional. And one very important value here, the address of entry point, is here. This is at the 12FF position. So we just put there a breakpoint. So practically, by the help of the BP command, you are able to set up some breakpoint. So BP, we copy here the base address, this one, and add this 12FF. Ctrl C, Ctrl V, and enter. We put a breakpoint to this position. Now we can let the application run, and it will stop at the breakpoint, so exactly at the entry point of the application. So I will use the run command, so debug go, and really it stops at the patching 01. Here is this security init cookie written here, or why it is written here now. It's practically only some cheating now, because if I go to this patching 01 directory and to this release, I left here this pdb file, the debug information file. Of course, in real situation you will have only the exe file, so you won't have this nice security init cookie and such a data, most probably. But now at least you are able to read that this first call is really just some security cookie initialization. Change a bit the size of the windows, this one. So it's not important for us. So we will step over it. So just run this call as a whole instruction. Run. Then here is the jump instruction. And as you can see, we are doing exactly the same like earlier in Olly. There are the same instruction, this push 10. And we just run it until we find a nice call. Nice call, which calls the main function. This is not that, because this is some interm e. So step over. Something else again. Interlogged exchange. Continue. And here it is. Now it is clearly written, patching main function is called. And it's exactly the same position like it was earlier, the 11b2. Now we press the step into. Now it is F11 or F8, just to be not the same like it was in Olly. The previous one was the F10. So we step into this call and we start to examine again the same code. It pushes some string to the stack and it will call the printf instruction. The first line is printed I continue, step over, again calls the printf. So the second line is printed. I continue with the step over. Here is the call scanf, so it will read something from the screen. Now it is waiting for my input. Come here, write here some number, for example 1, enter. And it is written, and now comes our nice comparison, so those two instructions. Now you can do again the modification. In case of WinDbg, it can be done by the instruction ep, the edit byte instruction, and we want to modify the byte at the position 010410 2e, and to the value 74. So this is the instruction what we want to run. If I run this instruction, first I show you just manually. I hit the enter, and you can take a look at this 75, it will change to 74, and really it changed to 74. So we can do it manually, but of course the manual work is good 1 or 2 times, but not always. So I change it back. We want to write again some script to do this modification for us, and we can use it many times. How to script the WinDbg? It's a nice task. First of all, I create here some directory for it. WinDbg script. And I will start here. The WinDbg has its own script language. It's quite interesting. And first we create some simple script just to introduce the language. So we will write the famous hello world application. Theoretically the extension of it is WDS, but of course you can use any extension you want, it doesn't care for it. And we open it with Notepad. And it's written on the following way. You can define blocks by the help of the dot block instruction, and you can use curly brackets to write the body of the block within those curly brackets. And the first simple instruction is the dot printf instruction, and in quotation marks, for example, we print the hello world text with some enter at the end and an exclamation mark to the end, just be nice. So I wrote a simple hello world script. How to run it? We can run it on the following way. We are here in the WinDbg command prompt. You write here $2 and greater than sign, less than sign, and you enter here the name of the script. So it is at C:\\WinDbg script, WinDbg script /hello world.vds. Enter, and it really printed the text hello world. Okay, let's write another simple script to practice how to use the variables. WDS, and let's try to add 2 numbers, or we can do it in WinDbg script. Again, we define a block, and if you want to use variables, you have to use the so-called pseudo registers. Those are the $T, and their counting starts from 0 until, if I could remember, 15. So there are many pseudo registers. And because it is a pseudo register, so it is a register, you have to use the command R. So this is the RT0 register. And we want to give it some value, for example, the 5. Similarly, if you want to give some value to a real register like EIX, it is written like this way. Okay, and now I use the other register, that's the T1. It will be some other value, for example 3, and we calculate the sum of these two, $T2 equals, you will write here $T0 plus $T1, it's almost correct. You have to put an @ sign before it to dereference them. And now we can print the result like .printf, and in quotation marks we print one number plus the second number equal, there will be the third number, and we write here the three registers, the $T0, sorry, instead of $T0 the @$T0, because we want to get the value, dereference it $T1 and $T2. Those are the values. So this is the second very nice simple application. File, save. Let's see how does it work. I call this variables.wds, and release print 5 plus 3 equal 8. So those are the basics of the WinDbg scripting. And now let's try to write a script which does the edit of this application automatically. So it will be called as p1.wds. WDS. And let's try to write it. Open with Notepad. First of all, we have to get the base address of the application. It can be done by the help of the command !LMI and patching 01, that's the name of this application. And as you can see, it prints you many information, and one of those information is the base address, and here is the value. Okay, the problem is that it will print you many applications. What we have to do is to find this line only. How we can do that? Unfortunately, in case of the, how is it called, the WinDbg, there is no string finding or things like that, but you are able to call operating system commands. So for example, we are able to call the find command of the Windows operating system. We have a nice find command here. Here it is. And practically it works on the way you have to give it some data what it should search for. So this string. So what we are going to do, we are going to run this command. So I put it to quotation marks and call the find command for all of its line, and we will search for the text base address column, maybe a space if you want. And the find is an operating system command. You can call it by the help of the .shell instruction. And to this .shell instruction you are able to add some data, for example the -ci to be case insensitive, if I could remember, -i, and we want the operating system to use the output of this data, so it will be the input of the find command. So this is the usual Linux redirection of the, like it is done in many Linux applications, the redirection of the standard output. So if we run this command, hopefully it prints only one line, the base address column and here is the required data. We got only one line, that's very nice, but now we have to get only this number and nothing more. As you can see, here is a text, practically one line, and we will need only the second column of this text. How to do it? We can do it on the following way. You can use the .for each instruction, and this .for each instruction has a /p switch, and here you are able to enter the number of the column, so we want to get the value from the second column only. And after that we want to get the values. Practically after that we don't need any values because this is all what we have. But after that, with the s, from every 10th, it's a huge number column, we want to get back the data again. Of course there won't be such a data, but it requires some way to add this value as well. So this is the p, how many columns leave at the beginning and how many columns leave after the beginning. And after that in brackets, we put this this instruction. Great, it's almost good. Just we have to put those instructions into curly brackets. Yes, like this one. And the result of this for each, as you know, in case of the for each, the actual value should be stored in a variable. We have to write here the variable. I will call it as obj, for example, like an object or something like that, but you can call it whatever you want. And after that, this for each will run and will give you back the actual values always in this object variables, and we are able to reference them in a cycle because the for each is a cycle. So I can put here some block and, for example, print f, the actual value, and it will be a %p, a pointer, and I want to print the $ curly brackets object variable. So this is how we can get the real value, and as you can see, it really prints only the required value. So we have the base address. It was a bit long. Now we can start the calculation. Here we were printing this base value. Now we don't want to print it, but we want to store it in some register. So we are just simply change this printf instruction to a register $, for example, T1 register. We store the value of the $ object. Great. And after that, when it was running, we are able to print. You can use the semicolon to separate the instructions. So after the cycle, there will be the number, and we can print it now to the screen. So printf, and we will print it as a hexadecimal value. And what are we going to print? It will be nothing else but the $T1. This is the base address plus 0x10(2e), because we have to change the value at the 10(2e) relative offset. Okay, and let's see how does it work. So I just put here some semicolon and run it again, and as you can see, now we got the address what we want to modify. Now we only have to do the modification. So we just printed this value, and after that we modify it a bit, because we not only want to print, but we really want to add this value. So we will modify it like $T1 equals this @$T1, so the value of it, plus 0x102e, and because it is a register modification I have to use the R command here. So now I added to the T1 the relative offset, and now I can do the modification by the help of the edit byte command. I want to modify at the position $T1, and I want to write there the value 0x74. Okay, and I copy paste it. It will be our nice script. Of course, here you are able to edit it a bit more, just to have some nicer look. Just a moment. It's a bit better. This way. Maybe easier to follow it. If I write like this. So we will get many data, the base address by the operating system's find command. The actual value, it will be only one, will be stored in the OBA variable. We need only the second column, and practically this one is required only because of the syntax, but won't be anything. Because of that, we will store the actual value in the T1 pseudo register. We add to this P1 pseudo register this 0x2e, does the relative offset, and we modify the data at the position of T1 pseudo register to 0x74. And now we can run it. You can run it by hitting the enter here, or just call the script. Maybe I will call the script. So $out in and C \WinDbg script /p1.wds. And now start to watch the value here. It should change from 75 to 74 if everything works fine, hopefully. And it really changed to 74. So we were able to write a simple script for the WinDbg as well to modify the application, to patch the application. And if I just run it, it really works as expected. If you debug, restart the application, restarted. I just run this patching code. Oops. Cannot be run because we are not at the breakpoint yet. So first of all, I have to put a breakpoint. Again, lmf m patching 01. This is the base address. Ctrl C and put a breakpoint. Sorry, first you have to get the information of the P header and then put a breakpoint to this address plus the program entry point. It can be seen somewhere. Optional header variables 12ff. 12ff. Breakpoint there. Then we can run until that. And now we can call our nice script. Most probably it is done now. And if I run it again, so debug go, it's running. Close this window because it just disturbed me. Asks for a number. I use, for example, the value 11, enter, and it prints really 0. So the application is really patched. So we went through the main debuggers what we are going to use. Of course, there are many other what you can use. but I want to use these three during this tutorial.